I'm going to solve a number of problems about computing the potential for a given charge distribution. So I'm going to start this problem because this is kind of the simplest. And so as a result, I'm going to illustrate some of the important points in here. So we have a charge Q distributed uniformly over a thin spherical shell, and with a given radius, and we would like to find the potential at an arbitrary point basically, but we are going to do the calculation separately for inside and outside. Right. Let's just see how we can solve this problem. Just keep in mind that there are actually two different ways to compute the potential. One is to integrate the potential due to the point charges. So in some problems, this may work. In some problems, it doesn't. So in this case, for example, since I have a distribution of charges over a sphere, to compute the potential at this point, for example, I need to do some kind of an integration over the surface of the sphere. And it appears like, this kind of a calculation is hopelessly too complicated. All right. So another approach is to basically use the definition of the potential. So that's the integral of the electric field. And it appears that since we know the electric field produced by this charge, it appears that we can compute the potential in here by using this procedure. All right. So it appears that in all problems with spherically symmetric charge distribution, this appears to be the best approach. Okay, so as a result, I'm going to solve it like that. Right? Let's just remember that, again, in the definition, this is not a formula for the potential. It's a formula for the potential difference. So as a result, at the end, you are going to compute a difference of the potentials in here. You can never compute the potential. So as a result, in all of these calculations, the first step is to basically choose a reference point. Right? Choose a reference point. Okay. We have, for at least for a point charge, we have just decided, we have used this convention that at infinity the potential should be equal to 0. So as a result, I'm going to follow the same convention too. So as a result, once you choose this reference point, then what you need to do is this. So that's my reference point at infinity. So that's the reference point. So I need to then choose a path of integration to the final point that I would like to compute. I would like to compute the potential at that point. So I need to choose a path, and over this path, I need to evaluate this integral. Right. So therefore, this is basically this is final minus the initial, and integration limits are basically from initial to final. Just keep this in mind. So in here the initial point is at r equals infinity. So let me, I don't know, let's just write down the little r and infinite value in here, so you would understand what I mean. So we have defined the potential at infinity to be equal to 0. So therefore, all I need to do is to evaluate this integral. If I want to compute the potential at a point with a radial distance r, all I need to do is to evaluate that integral. Okay. So obviously, in all of these such cases, so let's say that this is r, I'm going to choose the path to be a straight line that's starting from infinity and ending up in here. Okay, so at this point I can use some kind of a calculus techniques. For example, changing the integration boundaries. Basically, this corresponds to changing the path of integration in here, changing the initial and the final points. If I do that, then in that case the integral changes sign. So as a result, if I switch the places of these two, in that case, my integral becomes an integral with a positive sign in front, an integral from r to infinity. Okay, these kind of tricks work in here too. So don't worry about these kind of things. So, but just keep in mind that you're essentially changing the path direction in here, and you can easily convince yourself that this is actually this gives us the correct expression for the potential at r. What else? So at that point, I need to do some kind of I need to convert this into something integrable, some expression that I can use my calculus knowledge. So first of all, we write down the electric field as its radial component multiplied with the radial unit vector. I write down the radial displacement as this is the radial, the change in the radial coordinate. Let me write this thing again, multiplied with the radial unit vector. And so as a result, so the dot product of these two are basically equal to the product of the components, because this dot product is equal to R1, so that this dot product is equal to the product of the components. So V of R then is an integral from R to infinity of E dr. Okay, and I can use this technique for a point inside as well, but I'm going to come back to this, right? But let's first compute the electric field outside. So let's say it like this. So this is for a point outside the sphere, right? So in that case, I know that the electric field outside, well, I'm just going to write down the radial component in here. It is 1 over 4 pi epsilon 0 q divided by r squared. Okay, let's remember this. This is for any point outside, all right? I think I need to use some kind of a dummy variable in here. So perhaps if I call that distance as r prime, I need to write r prime in here. So in that way, this is the electric field at any point. So in any case, so I have a point outside in here. Its distance from the center is r, and I have a path in here that starts from this point and goes to infinity. And let's say that we have another point on that path. There's an electric field in here. So let me erase this. So if I then denote that distance from the center as r prime, then the electric field at that point is given by this expression. In any case, let's just quickly do the calculation. So I know that therefore this is an integral of from r to infinity of 1 over 4 pi epsilon 0 q divided by r prime squared dr prime. So some of you may get confused why I'm using this a different variable name in here, r prime instead of r, because r is just a fixed value in here. So I'm talking about a point at a distance r. So that's basically is a quantity that's defined at the beginning of the problem. It's not a variable, but I also need a variable that represents the position on that path. So as a result, I'm using a different name in here. So here, people call this r prime in here as the dummy variable. It's a variable that somehow appears inside an integral, but once you evaluate the integral, its value is irrelevant. All right, it's basically some kind of a variable that we use for carrying out an integral. But this r in here is usually called a free variable. That's something that survives all the time. In any case, so we have an integral of 1 over r prime in here. So let me multiply q. So the integral is minus 1 over r prime. So integration boundaries are infinity and r. So as a result, we get 1 over 4 pi epsilon 0 q minus 1 over infinity minus 1 over r. So at this point, there's no r prime left in the expression. And so as a result, the potential outside is 1 over 4 pi epsilon 0 Q divided by R. So that's basically the potential due to a point charge. This has to be something that has to be expected, of course, at the beginning. So it doesn't matter whether the charge is distributed over the surface of a sphere or it's just located at the center. I know that outside, the electric field produced by either of these is going to be the same. And so as a result, it's not surprising that for outside points, I get exactly the same potential due to a point charge. Okay, but inside, of course, the expression is going to change. Okay, so then let's pass to a point inside. So there are these two different approaches in here. So I know that, first of all, let me repeat this. I know that the electric field is 0 inside, and it has the usual inverse R squared expression outside. I'm just writing down the radial components of the electric fields. So that's the part that I need to integrate. So you can think of it like that. So that's as a function of the radial distance, the electric field has this kind of an expression. This kind of a plot. So outside it has the 1 over R squared behavior, but inside it is 0. So it's a function which is piecewise defined. I need to integrate this function. You can think of it like that. So as a result, you can still use the previous expression in here. So potential at R is, let's again remember where we started from. So it's that integral, and then we convert this as an integral from R to infinity of the electric field multiplied with dr prime. Yeah, there were also this dot product in here, but we also got rid of that. In any case, so as a result in here, I have a point which is inside, so somewhere in here. And so as a result, I need to integrate this function from inside to infinity. And so as a result, this function has places where it is identically equal to 0, and there are places where it is non-zero. Right? So as a result, you can then, for computing the integral of such functions, you can then separate this integral into these two parts. So first, I can integrate from this inside point to the surface, and then from the surface to infinity. Right? So therefore, I'm just going to write it down like that. So first of all, I need to integrate 0 from that point to the surface, and then I'm going to integrate 1 over 4 pi epsilon 0 q divided by r prime squared dr prime from r to infinity. So in a way, this integral is a little bit more difficult. So let me also show it on a physical diagram as well. So I have some point inside with a radial distance r from the center, and then I have a path in here. I need to integrate the electric field on that path, but in part of the path, the electric field is identically 0. Well, the electric field is piecewise defined on different parts of that path. So as a result, first, I need to carry out this path, this integral in here. And then from the surface to infinity, I'm going to carry out another integral. All right? That's essentially what it is. All right, so as a result, the first term is 0. The next term is, well, you can do the same calculation again, but usually people don't want to do these kind of things. So this is a calculation that I have done in the previous step. So as a result, there is no reason why I should repeat that thing. So that's essentially the potential at the surface of R, at the surface of the sphere. So I know that this is equal to V of R, and from the previous part, I have just computed this thing as 1 over 4 pi epsilon 0 q divided by R. Right? So that's one way of thinking about it, but usually people do it like that. So again, think of it like that. I have a point inside. Right? So let's say this is distance R, and I would like to compute the potential at that point. at this point in here. And what I need to do is to draw a path between this point and any other point in which I know what the potential is. And over this path, I compute the integral of the electric field. We have chosen the potential at infinity to be equal to 0. So this is a nice reference point. So you can always choose the path between infinity and that point. But in the previous part of the problem, I have computed the potential at every outside point. So as a result, there is no reason why I should extend this thing to infinity. I can choose any other outside point and stop there because I know the potential at that point. So I know the value in here. In particular, I know the value of the potential at the surface. So I know that this V of r is equal to 1 over 4 pi epsilon 0 q divided by r. And therefore, I can do it like this. So it's the same formula. Let me write down the formula again. So what I need to do is to basically start from this point in here at the surface and move along like that. So let me draw this with a different color, like red, for example. So I'm going to have a path in here that starts from here and end up in here, and it is in this direction. All right, let me erase and draw again. All right. So as a result, this is therefore potential at r minus potential at the surface. That's equal to an integral from the surface to the point of E dot dr. I always want to do the calculus integrals from, in the normal direction. So as a result, I changed the direction in here. So this is an integral from little r to capital R. So therefore, that means this path is now in the opposite direction. So let me erase again. In the final situation, I have a path starting from this point and ending up at the surface. In any case, of E dot dr, because of the same reasons that we have explained before, that's the product of the components of the electric field with the change in the radial coordinate. But the electric field is 0 inside. So as a result, this integral gives you 0, which then tells you that the potential at any point is equal to the potential at the surface. All right, this has to be expected. If the electric field is 0 in a region, the potential is constant in there. All right, so if it's in a region though, we can easily say this. So another way of thinking about it is something like this. We usually describe the thin spherical shell as some kind of an abstract charge distribution, but if I have some kind of a metal sphere, a conductor, and if I add a charge to that metal sphere, no matter how I add it, I know that in static equilibrium, all of this charge will be distributed uniformly over the surface, because that's the only distribution that will produce 0 electric field inside. In any case, so the charge will be distributed over the surface, and I know that because of that, the electric field inside the conductor is 0. It has to be 0. And so therefore the potential is constant on a conductor. Again, this is in static equilibrium, meaning that there are no currents. Okay, so therefore I'm going to draw this again. The electric field as a function of the radial distance. I don't need to use r prime in here anymore. And then the potential due to this. So I'm going to use a thick color in here. So the electric field, inside it is 0. Let me make it a little bit thicker. Outside it has the usual 1 over r squared behavior. So it goes to 0 like that. So the electric field outside is proportional to 1 over r squared. For the case of potential, outside potential is proportional to 1 over r, the point charge result, but inside it is constant, and the value of the potential is basically equal to the value of the potential at the surface. All right, so the derivative of the potential gives you the electric field. Since the potential is constant in here, inside the sphere the electric field has to be 0 too. One important point in here is that the potential can never have a discontinuity. So you cannot have any situation like, I don't know, let's say it like this. So in a potential versus R graph, for example, you can never have a situation like that. We cannot have a jump discontinuity in the potential. Try to understand what this means. Because the derivative of the potential with respect to the radial coordinate gives you the electric field. You can think of it as a line with an infinite slope. So as a result, this would then correspond to a situation where the electric field is infinite. In a model situation, for example, in a mathematically idealized model, perhaps you might meet these kind of situations. But you know what the problem is. I mean, you have to use your physical intuition at this point. So do we have a charge distribution in here that would produce this much electric field? In most of the examples that we are going to solve in that course, we will never meet these kind of situations. So we won't have like places where the electric field goes to infinity, except if we have a point charge or anything like that. But you know that the potential goes to infinity in there. So in any case, so we won't have any situations where the potential is discontinuous. So as a result, you can safely assume that potential is always continuous, except at places where it diverges to infinity, obviously, for point charges and things like that. Okay, so let me stop here.